Hello everyone and welcome to the next video in the series. This is a technical skills video on the topic of theoretical equations that involve a mix of the basic operations. Now in the previous two videos I did give an introduction to the art of solving equations, and you should watch those two videos before you look at this one. Because again, a lot of background information is given in those videos, and in particular I talked about the algorithm for solving a linear equation in one unknown, with the unknown appearing only once throughout the equation. Linear equations are equations in which x, the unknown, is being either added, subtracted, or multiplied, or a combination of these. In the previous video I talked about each of these operations individually. And now I want to talk about the kinds of equations where multiple operations of this kind, addition, subtraction, multiplication, appear. Now the steps remain the same. We solve for the term that contains the unknown, and then for the factor that contains the unknown, and then we repeat steps 1 and 2 until we're done. And I did talk about what it means to solve for something in the previous video. And also I talked about two different approaches to solve for the term or the factor or whatever it is that you want to solve for. And these two were named natural semantics. One of them follows the kind of logic that we call natural semantics, which says that an operation on one side can turn into its opposite on the other side. And the other one was called, is the kind of logic that uses, that we call standard semantics. And this one says that if you have an equation, you can do the same thing to both sides of the equation. Now I did give my reasons for why natural semantics is superior. It's both more efficient and also more meaningful. And so in these videos I will be following natural semantics. Okay, problem number 1. The equation is 3x plus 5 is equal to 11. And step number 1 is to solve for the term that contains the unknown. That would be 3x. Now we see the problem as 3x and then add 5 to get 11. And you notice that I didn't say we begin with 3, then multiply x, then add 5. I said we start with 3x, then add 5. And the reason for that is because in step number 1, our focus is on terms. And so we start with the first term, which is 3x, and then we add the next term, which is 5, and we get 11. Now, in order to solve for the term that contains the unknown, that would be 3x, we need to get rid of plus 5. And following natural semantics, we take plus 5 and move it to the other side of the equation and make it minus 5. Now we can simplify. Simplification means if you can add, subtract, multiply, or divide any numbers, you should do so. And in this case, I can do 11 minus 5, which gives me 6. All right, and we see this as 3 times x, of course. Now we have to decide what to do with 3 next. This is step number 2. Solve for the factor that contains the unknown. And when we talk about factors, our focus is on multiplication and also division by a number. And therefore we see the problem as times 3 times x, which would be 1 times 3 times x, of course. And because 3 is being multiplied on the left side, we divide by it on the right side. And we get x is equal to 6 divided by 3. And now we simplify to get x is equal to 2. Alright, so this flavor of natural semantics is called natural semantics with intermediate simplifications. And the reason is because we take one logical step, solve for the term that contains the unknown, then we simplify. We do 11 minus 5. Then we take another step, logical step, solve for the factor that contains the unknown, and then we simplify. We do the division. So simplification is appears at every other step, if you like, at least for this problem. There is a different approach in which simplifications are left at the end. So initially we follow step 1, solve for the term that contains the unknown, but we don't simplify. We don't do 11 minus 5, 6. We just keep it as 11 minus 5. And then we solve for the factor that contains the unknown. Once x is isolated, then we start simplifying the equation. Following this approach, we write down 3x plus 5 equals 11. So again, we start with the first term, which is 3x. Then we add 5 to get 11. And we want to solve for the term that contains the unknown. So we put down 3x equals 11. We take plus 5 and turn it into minus 5 on the right side. But now we don't simplify. Now we solve for the factor that contains the unknown. And that would be, we have to get rid of 3 now. We have to solve for x. And so again, we see 3 as 3 times x, or times 3 times x if you like. And because 3 is being multiplied by on the left side of the equation, we divide the right side by it. So you see, I didn't simplify 11 minus 5. I'm just keeping it as 11 minus 5. Divide by 3. So all the logical steps have been taken now. We solved for the term that contains the unknown. That's 3x. And then we solved for the factor that contains the unknown. That's x. And now we start simplifying. To simplify, we have to do 11 minus 5. And then we divide by 3. Now, the first approach is more efficient, but the second one is one that you should know. Because when it comes to formulas, usually simplification is not possible because we don't have numbers, we have quantity symbols. So for example, if you have, in place of 11, if you have y, and in place of 5 you have z, then you can't really work it out. You have to just keep it as y minus z. And so this approach is a good one to know as well. Both flavors are important to know. I would say that the one that's most meaningful and gives you most power, if you like, over understanding what it is that's happening is actually the second one. Although the second one, because we don't simplify, things can build up, and after a while your equations can become a little bit sort of like long, if you like. But anyways, I do recommend that you know both of them. Okay, problem number 2. 8 minus 5x is equal to 3. And we follow, let's say, natural semantics with intermediate simplifications. And so we see this as 8 minus 5x, which would be plus 8. And of course, that's 0 plus 8, if you like. So 8 is being added. 8 is not being subtracted. 5x is being subtracted. 8 is being added. And we take addition by 8 on the left side and move it to the right and make it subtraction by 8. Keep in mind that the subtraction sticks to 5x. So we end up with negative 5x is equal to 3, and then we subtract 8. All right, and now we can simplify. 3 minus 8 is negative 5. Now we solve for the factor that contains the unknown. And now our focus will be on multiplications and divisions. And we see negative 5 times x as times negative 5 times x, or if you like, 1 times negative 5 times x. And multiplication by negative 5 on the left turns into division on the right side by negative 5. Now we simplify, and we get 1. So we solved for the term that contains the unknown, simplified, solved for the factor that contains the unknown, simplified. Now, if we follow natural semantics without intermediate simplifications, then 8 minus 5x being equal to 3, we still have to see this as plus 8. 8 is being added. And we solve for negative 5x, which becomes 3, and then we take plus 8 and turn it into minus 8. But now we don't simplify. We don't carry out the subtraction 3 minus 8. We just leave it like that. Next, we solve for the factor that contains the unknown, and now we focus on multiplications and divisions. Negative 5 times x, we see it as times negative 5 times x, which comes from 1 times negative 5 times x. And because negative 5 is being multiplied on the left, we divide on the right side. Now that we've taken both of our steps, both of the logical steps, solve for the term that contains the unknown, solve for the factor that contains the unknown. Now we simplify. Working out the top, we get negative 5, and then negative 5 divided by negative 5 is 1. Okay, problem number 3. Negative 2 minus 3x is equal to 4. Here is natural semantics with intermediate simplifications. Now this time I'm not going to use color coding. So we've got two terms, -2 and 3x, and we solve for the term that contains the unknown. The subtraction here sticks with it, and so we get -3x is equal to, keep 4, and then we turn subtraction by 2 on the left to addition by 2 on the right. Now we simplify. 4 plus 2 is 6. Now we solve for the factor that contains the unknown, and that would be x. And because -3 is being multiplied by on the left side, we divide by it on the right side, and x becomes -2. So we solved for the term that contains the unknown, simplify it, solved for the factor that contains the unknown, and simplify it. And here's the solution following natural semantics without intermediate simplifications. So here again we have to solve for the term that contains the unknown, and we have 4, and then we move subtraction by 2 to the right side and make it addition by 2. But we don't simplify. We don't carry out 4 plus 2 equals 6. We continue with the logic. We move on to step number 2, and we solve for the factor that contains the unknown, which is x. And because -3 is being multiplied by on the left side, we divide the right side by it. Now we simplify the top, and then divide by -3. So here we solved for the term that contains the unknown, then the factor that contains the unknown. Then we simplified. Okay, problem number 4. And of course the numbers can be natural numbers or integers or rationals or even real numbers of any kind, and the steps are pretty much the same. So here as well we solve for the term that contains the unknown. That would be 1/2 x. Keep in mind that the subtraction sticks to it, and also keep in mind that 2/3 is being added. There is a plus here. So we solve for the term that contains the unknown, and we get -1/2 x equals, we keep 11/15, and then we turn addition by 2/3 into subtraction by 2/3. Now we simplify. On the right side, least common denominator is 15. Now this step of simplification has nothing to do with algebra really. This has to do with your ability to add and subtract rational numbers. And then 15 divided by 15, 1, times 11, 11. And then we subtract 15 divided by 3, 5, times 2, 10. And we end up with -1/2 x is equal to 1/15. And in the previous video, we argued that now solving for the factor that contains the unknown, because we are multiplying by 1 and dividing by 2, and the negative sign can be associated with either. On the right side, we do the opposite. We multiply by 2 and divide by 1. And of course, the sign again, whether you put it on the top or the bottom or the side, in the end, it will be a negative number. Now we simplify to get x is equal to -2/15. Okay, problem number 5, one more with fractions. Solve for the term that contains the unknown. I'll let you actually see if you can sort of follow the logic. If you like, you can pause the video and think about what happened here. And then, at this stage now, we need to solve for the, so basically what we did was we solved for the term that contains the unknown. Now we want to solve for the factor that contains the unknown. And this time I'm going to do the solution without intermediate simplifications, and let's see how it works. So I'm not going to add 7/12 and 3/4. Because we are multiplying by 2 here and dividing by 3 on the other side, we do the opposite. We multiply by 3 and divide by 2, and then we multiply all of the right side by it. Now that we have taken step 1, solve for the term that contains the unknown. Step 2, solve for the factor that contains the unknown. Now we simplify. We add inside the brackets, least common denominator is 12. 12 times divide by 12, 1. 1 times 7, 7. Then add 12 divided by 4, 3, times 3, 9. Simplify the top. And now we can reduce 3 and 15, 2 and 16. I let you do that. And in the end we get, that should be negative. So let me put the negative sign in. There we go. And wow, it became bigger even. So there we go. We get -8/5. Okay, next problem. Now, problems that have brackets in them, there are two approaches for these, and one is way superior. And I will have a lot more to say about why is it that the first approach is better than the second one when we talk about applications of these kinds of equations in the next two videos. But here I just introduce both of them. I will make a brief comment about why the first one is better, but more detail, a lot more detail in the next two videos. So here, following the steps that we have, we solve for the term that contains the unknown, and that's been done. There is only one term on the left side. This whole thing is one term. It has two factors. 4 is factor number 1, and the bracket is factor number 2, or what's inside brackets is factor number 2. Basically what we are doing is multiply 4 by brackets. So there are two factors, and we want to solve for the factor that contains the unknown, which is x plus 3. And because 4 is being multiplied by on the left side, we divide the right side by it. Now we simplify. And now we are back to step number 1. When you open up brackets, usually that happens. If you have multiple terms inside them, you go back to step number 1. So here we solve for the term that contains the unknown. We'll take plus 3, move it to the right side, and make it minus. And now we simplify. Alright, so this is one way to solve this problem. The alternative, which is not recommended, but unfortunately it's pretty common, is for people to multiply the number into the bracket. This approach is useful when there are multiple terms with multiple brackets and there are multiple instances of x. If x appears only once, then this approach that I just gave you here is much superior. And the alternative, which is not recommended, at least for this problem, is to multiply 4 into the bracket. And of course, if you want to quadruple a sum, you can quadruple each of the terms and then add them. So 4 has to multiply both x and also 3. Right. So 4 times x becomes 4x. And then 4 times plus 3 becomes plus 12. Now we solve for the term that contains the unknown. So back to step number 1, or we go to step number 1 now, and we solve for 4x. Plus 12 moves over, becomes minus 12. Simplify. And then solve for the factor that contains the unknown. Alright, so why is it that the top approach is superior? The reason is because in applications it makes more sense to follow this approach, because this approach sort of falls into the way we would naturally reason. So here, to give you an example of that, I'll put a word problem to this equation. Let's say there is a box. Inside the box there is a pen, and the price of the pen is unknown, and there is a notebook, and the price of the notebook is $3, and we want to find out what the cost of the pen is, but we know that the cost of 4 boxes is $20. In going from here to here, we find that the cost of 1 box is 20 divided by 4, or 5. You see how that works? We start with the cost of 4 boxes being $20, and then we find the cost of 1 box being 20 divided by 4, or 5. This approach follows a different kind of logic. It says if you have a pen with an unknown price of x and a notebook with a price of $3, then the total cost of all the pens would be 4 times x, and the total cost of all of the notebooks would be 12, and then subtracts 12. Apart from the fact that numbers get larger, normally this is not the way we would reason. I highly recommend that you follow this kind of logic. Especially when problems become difficult, you should definitely see. If you think that this approach is better, you should for sure take a look at the videos that follow. When I talk about applications in detail, such as the boxes that I just talked about. But these applications are much more interesting and more complicated. We'll be talking about, let's say, the masses of molecules. And you'll see how beautifully this logic follows the kind of logic that goes into the solution of those problems. Now again, you might say, so under what conditions do we multiply the number into the bracket? And as I mentioned a little bit earlier, under conditions when your equation has multiple brackets or multiple instances of x, you don't have much of a choice, and you will have to multiply the number into the bracket. Okay, problem 7. 5 times x minus 4 is equal to 10. We solve for the term that contains the unknown. That's already done. Then we solve for the factor that contains the unknown, which is the bracket. 5 is being multiplied by on the left. We divide by it on the right. Simplify. Now we go back to step number 1. Solve for the term that contains the unknown. Subtraction by 4 becomes addition by 4 on the right side. And then simplify. Here's the alternative. Multiply 5 by x to get 5x. Multiply 5 by 4 to get 20. So actually it's 5 times negative 4, so the sign is important too. And now we solve for the term that contains the unknown, 5x. Subtraction by 20 becomes addition by 20 on the other side. Simplify, and then solve for the factor that contains the unknown. Alright, problem 8. Now, you might argue anyway that one of the drawbacks of this approach is that you may end up with fractions right away of the better approach. So in the sense that if I now solve for the factor that contains the unknown, the term is already done. If I solve for the factor that contains the unknown, I get 5/4. With the previous problems, we were lucky that the division could be done and you would get a simple number. But now, of course, we don't want decimals because decimals have to do with applications. This is a theoretical discussion, and we stick to the formal notation, an exact descriptive notation. So now we have to solve for the term that contains the unknown. Addition by 3 becomes subtraction by 3. But now we have to do the subtraction of fractions. And some people might complain about this. But my answer to them is instead of trying to change the kind of logic that's so natural and so efficient, why don't you fix the problems that you have with fractions so that they're not such a headache all the time? And if you're good with fractions, then this solution is very easy to write down. The alternative solution would be to multiply 4 by x to get 4x, and then 4 times 3 to get 12. Solve for the term that contains the unknown. Simplify. Solve for the factor that contains the unknown. And we get -7/4. Alright, we have, I believe this is the last one for today, if I'm not mistaken. So again, we solve for the term that contains the unknown here. My apologies, the term has been done already. There is only one term on the left side. We solve for the factor that contains the unknown. And again, there are two factors here. -3, that's factor number 1, multiplied by the bracket. And the bracket is factor number 2. So the factor that contains the unknown is the bracket. And because -3 is being multiplied by on the left, we divide by it on the right side. Simplify, and then solve for the term that contains the unknown. Simplify. The alternative, we multiply -3 by -4 to get 12, positive 12, and then -3 times plus y gives us -3y. And then solve for the term that contains the unknown. Simplify. Solve for the factor that contains the unknown. Simplify. Okay, everyone, thank you so much for yes, there is one more. I knew that. Okay, so here we have brackets within brackets, and actually this one is pretty interesting. The whole thing again is one term. There are no additions or subtractions outside brackets. And it has two factors. -3 is 1. That's being multiplied by the square brackets. What's inside the square brackets? So square brackets make up factor number 2. And we solve for the factor that contains the unknown. Multiplication by -3 becomes division on the right side. Simplify. And then solve for the term that contains the unknown. Now we have two terms. 5 is term number 1. and 3 times x plus 4 is term number 2, and the subtraction sticks with term number 2. So we take addition by 5, that would be plus 5 over here, and turn it into subtraction by 5 over here. Keep in mind the subtraction sticks to the term that follows. Alright, now we solve for the factor that contains the unknown. And there are two factors here. There is x plus 4. My apologies, I did do simplification. And now we solve for the factor that contains the unknown. And there are two factors, negative 3 and the bracket. We solve for the factor that contains the unknown, that would be x plus 4. Negative 3 is being multiplied by on the left. We divide the right side by it, and then simplify. Solve for the term that contains the unknown, and simplify. Okay everyone, that is the end of this video. And in the next two videos, I will be talking about how do we deal with applications when these equations appear in applications. That's where decimals come in, because in applications, we measure values. And when we measure values, we cannot be exact. We don't have to be descriptive. And decimals are the best notation to use in such situations. Take care everyone.